All right. Before we start, I posted the submission for checkpoint 1 for the, hold on. Oh yeah, that's fine. So we are asking you to drive the little maze that we have in the lab at a slow speed, about 0.2 meters per second, and then a fast speed, about 0.8 meters per second. And take a video of both times, and then also record the odometry data, and then plot that. And then the other thing we're asking you to do is fill out a form that just report the status of your robot, whether it's fully functional or there's problems, and you can report the problems. And then report the calibrations that you took with our calibration procedure. So the forward and or the negative and positive wheel calibrations for any motors that you have. And so you can just put in comma separated values for that in the Google form. And then we'll see how much variation we have in our motors. It'll be interesting to see. Yeah. Yeah, so for the form, just submit it individually. I'm mostly just collecting information from you. For the submission on Canvas, yeah, do 1 per team. So you only need to do it with 1 robot. So even if your team has 3 robots, you know, take your best one and get it working. Okay, we're not worrying about that. But at this point in the lab, we're done with covering the material on the sort of low-level control and driving. So we've given you a motion controller, which, or we've given you a wheel controller, which we've asked you to update. And so most of you, I think, are well on your way to tuning those PIDs. We've given you the motion controller, the super basic rotate, translate, rotate motion controller. And so you should be updating that to fit your needs. But if in both cases for the checkpoint, if you aren't there yet, you can just use the stock controllers and try to do the checkpoint. So the next phase of this lab is to move on to localization, mapping, and navigation. And so today we're going to look at an sort of intro to the probabilistic robotics problem, and then specifically how we're going to build a map of the environment for our MBOTs. All right, so probabilistic robotics really took off in the early 2000s. And this book, which there are excerpts from on the Google Drive for you to read for this lab, is sort of the seminal textbook on methods in probabilistic robotics. Just about anyone you ask here will have this book in their office, okay? So the idea is that we're going to explicitly represent, right, uncertainty using probability theory. And so as an example, if we're trying to represent, say, the location of a robot in our environment, instead of just representing that as a point, we're going to be representing that as a multivariate distribution in, say, the degrees of freedom of our robot. So in this case, X and Y, because it's really hard to show a 3D multivariate distribution. But right, our robot location is going to have some error in X and some error in Y. We can model this as like a Gaussian distribution. And then a position of our robot will have, we'll assume it's the center because that's the maximum probability, but we'll have explicitly represented how much uncertainty we have in that measurement. And we can do this for both continuous functions, which you would do with what we would call EKF slam or some other sort of Kalman filter slam, or we can do this with discrete values. So what we're going to be doing in this class is representing the position of our robot using a particle filter. And so each particle is going to be a pose or a point in this. And when you take the ensemble of all of those poses, you get a distribution, a discrete distribution in X, Y, and theta, because that's our configuration space, right? On the ground, we're just moving in 2D, so we have 3 degrees of freedom, X, Y, and theta. And so when we do localization and mapping with uncertainty, our world sort of looks like this. We have a robot here, but our probability of it being there is something like 0.15. And then for every sort of cell in our environment, we have some prediction. This is most likely free space, so the probability that it's an obstacle is very small, like 0.005, and this is most likely a wall, so the probability that it's an obstacle is large, right? Something like 99.5%, 0.995. And then for anything we have not observed, we don't know anything about it, and so the probability that it's occupied is a coin flip. It's 50%, right? We don't know anything about it, and so it could be occupied, it could be unoccupied. We don't know. So in probability, we have to worry about continuous random variables. So we have some continuous random variable X that can take on any value in the continuum. And then we want to know the probability that that variable X is a value X, right? So we'll use capital X for the random variable, lowercase x for the value that we're testing, right? And so that we have probability of X being little x is our function. And that is our probability density function. And because it's a probability, it integrates over all X to 1. So we care about that it integrates to 1 over all values. Similarly, we can have a discrete random variable, right? And so the probability that X takes on some value X sub I, right, is just the size of this one bar in your histogram, okay? And so this is called a probability mass function. We can take on a discrete values in this, but still, when we sum up all of the discrete values, they all sum to 1. From this, we need to talk about joint and conditional probability. So not only can we have a probability in one variable, right? We can have a probability over multiple variables. So the joint probability is the probability that X takes on some value X and Y takes on some value Y. And we can write that as the probability of X comma Y. If they're independent, right? If X and Y are completely independent, then that joint probability is just going to be the product of the individual probabilities. But if they're not independent, we can talk about the conditional probability. So the probability that X is X given Y is Y. All right, so the probability of X given Y is going to be the joint probability of X and Y divided out by the individual probability of Y. And similarly, we can rewrite this as the joint probability of X and Y is going to be the conditional probability of X given Y times the individual probability Y, right? And if these are independent, if these are truly independent, right, then the probability of X given Y is just going to be X. Because it doesn't matter what value Y takes on. So then we have the value, the discrete case, right, where we're talking about probability mass functions, the continuous case where we're talking about probability density functions. In the discrete case, the mass function sums to 1, right? And in the continuous case, it integrates to 1. And then if we want to know what the probability of X is, we can just sum over all of the possible values for Y, right? And get the probability of X. Similarly, we can do that for the joint probability, and we can also do that for the conditional probability. And then you have the continuous cases the same. All right, so how are we going to use this for mapping? Well, mapping is this fundamental problem that we have, and since our environment is uncertain, we need to have an explicit representation of that uncertainty when we create a map. When we use these maps, we use it for lots of different things in robotics, right? We use this, we need maps for localization, we need maps for navigation, and we need maps for planning tasks as we go. So the same map can have different representations, right? So in these sets, which is a map that we've made of the grove over there, right? We have a map that we can use that looks at the vertical features, where we can see features in the environment and we can locate ourselves relative to them. You can see Laurie Tower right there as the square. We also have to have a map then of the path that is free and open that we can drive on, right? So we have this map, which shows the free areas that we're able to drive. We can turn this map representation into a grid, or a graph, which we can then use to very quickly navigate between points, right? So all of these map representations are used for different things, and they're optimal for different tasks or different algorithms, but each has some explicit representation of uncertainty in it. Other maps you might sort of see, right? Those were what we call occupancy grid maps, where we're measuring whether cells are occupied or cells are free. But we can also use maps in different forms. This map is just a dense 3D point cloud where all of the measurements of the environment have been mapped to a real position in 3D space, and then we can use that for navigating. You might have a sparse set of 3D features. If you're doing some sort of optical visual SLAM, like orb SLAM, you're measuring features in the environment that are very distinct, and you can identify easily between frames, and then mapping those into 3D space and using that as your representation of your space. Similarly, you don't have to have just metrical maps. These are all metrical maps. They indicate, the spatial relation between things. You can also have a hierarchical structure in your map where you have both metrical maps and semantic maps, and you can sort of have different layers in your map depending on which plan. And this is the kind of map that the semantic mapping system Hydra makes. So for this class and for this lab, we're going to be using occupancy grids. So an occupancy grid is just an array of cells, right, that represent some point in space. So it's going to be an M by N matrix of cells. As space grows or those cells are smaller, you can have more or fewer cells. And the idea is that the cell is the actual cell, right? That actual position in space is either occupied or unoccupied, but we don't know that, right? We don't know whether it's occupied or unoccupied. So what we're going to do is we're going to observe it, and we're going to calculate a probability that that cell is occupied or unoccupied, right? If we haven't observed it yet, what's the probability going to be? Yeah, 1/2, right? But as we make more observations of the map, right, we're going to be more confident that a cell is occupied or more confident that a cell is unoccupied. And so that value will go down or up depending on the state of the cell in the map, okay? And so what we're going to do is we're going to infer what the map is using what's called a Bayes filter. So using all of our sensor data in this Bayes filter, we're going to calculate the probability that the map is the true map. The map, our representation is the true map, given all of our sensor measurements, right? And where we were when we took those sensor measurements. So this X of t, that's the pose of our robot. And then Z of t is going to be our sensor readings of the robot, so the LiDAR scans. All right, and so we're going to use a Bayes filter, and it's based on Bayes rule. And so Bayes rule is very powerful for prediction. The idea is that if we have some quantity that we want to infer from some new data, we calculate then the probability A given the new data B. And so the probability of A here from Bayes rule is the prior probability of A. And then we're going to try to calculate this posterior probability of A after taking this new data into account. So this this term here, the probability of B given A, is basically the likelihood that we're going to get B, in this case, say a sensor measurement, given A, in this case, our map, right? And then this probability B is just some sort of prior probability that normalizes this, because if we sum over all possible A's, right, this needs to normalize to 1. And so to make a Bayes filter, we have a stream of observations of our environment, in this case, laser scans, and we have a stream of action data. So we have the pose of our robot as we moved, and we have the laser scans that we took at each of those points. And we're gonna make an observation model, what we call a sensor model. That's the probability that we're gonna get some sensor scan given that we're at some position X, right? The probability that the sensor scan we got was generated by the position we were at. And then we'll have some action model. In this case, the probability of being at some position given some past actions that we took. And then we'll have a prior probability of the system state that we're trying to update. And so what we're going to try to do is estimate the new state of this system. And the posterior, we're going to call the belief. So our belief in our pose in this case is going to be the probability of this pose given all of the actions we took, U1 through UT-1, right? And all of the sensor measurements we took, Z through Z at time T, all right? And we can calculate this using this form. Now, this seems daunting, but it's actually not that bad because we can make the Markov assumption. So we make a few underlying assumptions about our system, and then we can just make this simple step to basically just updating it at each time step. So the underlying assumptions are we have a static world, like that's not changing. And now that's not a great assumption, right? If you have obstacles in your environment that move, pedestrians, things like that, that's not a good assumption. But we can actually we can treat those separately, and that's fine. And then the other assumption is that given the present, right, it's independent of, the future is independent of all the past, right? So we are only caring about the next step is only dependent on our current state. It's not dependent on the history of our states. All right, so we only need to look at our current state in order to generate our next state. So given that we're in the state X, this sensor observation Z is independent of what happened before, okay? And so in that case, we can just step through and update our model at each time step. So given a set of robot poses, we're gonna make a map now. Given a set of robot poses that we know, X0, X1, X2, and then the laser scans that we got while at that pose, Z1, Z2, Z3, so on, we're going to infer what this map is, right? We don't know what this map is. This is a latent variable. We said that it has some form, but we don't know it. We're gonna check, we're gonna basically calculate what it is and update our estimate of what it is as we get new poses and new sensor information. And so we can express this probabilistically, right, as the probability that we're gonna get the true map given Z, our sensor readings, and our poses, our positions in space. And from this, we can build this occupancy grid. So we need our poses. For each pose, there's going to be a set, right, of laser returns. And as we drive around, we'll see more of the space and more of the laser returns. And as we add them all up, we get this nice occupancy grid map where unknown space is gray, free space is white, and obstacles are black. All right. Another thing to know, if we're just using probabilities, as we go closer to occupied, right? This number is just going to get closer and closer and closer and closer to 1. And as we get closer to free, that number is just going to be closer and closer and closer to 0, right? And so numerical precision becomes an issue when you're trying to compare whether it's, say, 99.999% confident that it's occupied or, adding more nines. And so the better way to analyze this is, instead of using the probabilities, is to actually use what we call log odds. And so the odds of it being occupied, right, are just going to be P of A, right? And then the odds of it being, or sorry, not the odds, the probability is occupied is the probability of A, right? Then the probability that it's free is going to be just the inverse of that. So the probability not A. And so then the odds of it being occupied is just going to be the ratio of the two, right? So the odds of it being occupied is probability of A divided by the probability of not A. And this is going to have some range like 0 to infinity, right? So either, yeah. Then if we take the log of this, we get what we get the log odds. And so we're moving a scale that goes from 0 to infinity and can go to infinity fairly fast, right? If the probability of it being occupied is large, then the probability of being not occupied is very small, right? And this number is going to be very large. That's going to be hard to deal with. So what we want to do instead is use the log of that to calculate. And now technically this has a range from minus infinity to infinity, but it grows much smaller, right? So even if something has an odds of being occupied of, say, 2 to the 100th power, right? The log odds is only going to be 100. So a reasonable, usable number that we can use in our map. And so for our map, each cell in our map is going to hold the value of the log odds that it's occupied. And so that means that 0 is going to correspond to it being unknown, right? A probability of it being occupied of 1/2. As the number is positive, it becomes it's more likely occupied, right? And as it becomes negative, it's more likely free. And so if you reformulate Bayes' rule with odds, and you just need to take the ratio of, right, A given B and not A given B, which gives you the odds ratio. So we define this as lambda of B given A. And we can take the logarithm of that at any time. But in this form, in the form of the odds, we have some odds of posterior A given B is just going to be this lambda B given A, which is our sensor update, and the prior odds of A. And so what we need to do, if you take the logarithm, right, we have the log odds of A given B times the sensor update, the log of the sensor update plus the log of the prior. What that means is that we can just go through and step through, take our previous estimate of the cell, right, add our new sensor information just as a number, and get the output of the cell. So it looks like this. We have some prior map, right? That's P of M. And then we calculate some sensor model for each time step, right? So that's log of lambda of the probability of getting that sensor reading given the position in the map. We just add up subsequent sensor updates and get our posterior map. And that's how we're going to be building this map for the lab. So how do we know what the sensor model is? How do we know how to update those log odds as we get new information? Well, so if you were to just sit your robot down in a place, pointing at a wall or something, and just measure what data was coming out, what ranges were coming out of your LiDAR, you would get a distribution something like this. All right. And so we want to know then how this can turn into a sensor update. So this distribution is really just the sum of a bunch of different distributions. All right. So we have the probability that it's a hit, right? That's that peak. So that the laser range that we got represents the true distance to an obstacle. And that laser has some error, right? There's some uncertainty in the laser rangefinder that gives some error. And so that's going to be the width of this. So we have a Gaussian model for the error in our laser range, all right? And then we have this distribution moving up to the distance we measure. And this is measuring basically that the laser hit short. And so the probability that the laser, we get a return that's actually before the actual obstacle is going to be something falling off exponentially from our minimum. Now, what would cause this? Well, this would be like random people walking in front of our robot that gives us a bad measurement, right? A measurement not of the environment, but a measurement of something, but it's not the map that we're interested in, right? So there's some probability that we're going to get, someone walking in front of our robot and giving us a spurious, incorrect measurement for that sensor reading. We have then the probability that we just get a random measurement that makes no sense, all right? I don't know, the electronics did something weird, the sensor physics did something weird, and we just get a random measurement. That's our uniform distribution, p random. And then also there's a probability that we're going to get whatever the max range of our sensor is. And that's actually a fairly large probability, because that would happen if, say, our laser bounced off something reflective and went off in a different direction, and we didn't actually see its return. We might think it's hitting the max, okay? And so if you add all these together, you get this weird sensor model distribution that looks like this, all right? And so what we can then do is look at what the values are and determine what we should do to update our log odds. All right, so if our laser terminates at some value, right, some distance d, we want to increase the log odds because we have a new sensor measurement that says that's an obstacle. But how much should we do it by? Well, we need to look at, right, the probability that it was a true distance measurement, given that it was occupied, right? Or the probability of getting that measurement D given the cell was occupied, divided by the probability of getting that measurement D given the cell was not occupied. All right, so that's like saying, what is the ratio of this value, right, to the value anywhere that's not this, okay? And so that's going to be like, say, 0.06, maybe it's the height of that distribution divided by 0.005, 12, and then we take the log of that, right? That's the odds. We take the log of the odds and get some number, 3.5. So our laser hits a wall, bounces back, we get a range measurement. Then we can say, okay, at that point in our map, we're going to increase our log odds by 3.5 because we have a new sensor measurement that says that that's occupied. But we're not 100% confident that that's occupied because there's other ways, right? There's other ways that we can get that range reading. Similarly, we can do the same as it passes through the cells, right? If the laser passes through the cells, we also have information because we know that those cells are free because the laser was able to pass through them, all right? And so we can decrease the log odds for those cells based on the ratio. And, we sort of choose by looking at, right, how much of this distribution we would have if we got that, if we pass through some cell, like what the probability of doing that versus probability of passing through when it is not occupied, right? And we'll get some number and we can take the log odds. Now, in effect, in the algorithm, these numbers are just constants, right? And you can just tune them for performance. So you can be very careful about measuring your sensor model and figuring out what these should be. But in the end, you can just, they're not very sensitive to changes because they're the log of a number. And we can just choose some value to increase or decrease the log odds based on how well the robot performs in making a map, okay? And so in effect, these are just tuning parameters for our mapping system. All right, so to implement this, for each valid laser ray that we get, we're gonna convert that laser ray, right, into some pose where we started the pose of our robot into the start cell in our map. And then we're gonna figure out where that reading was, the end cell in our map. For the end cell, that's where we got the return, right? We're going to increase the log odds. It's gonna be more likely to be occupied. For all of the cells that we pass through, we're gonna decrease the log odds, right? Because we have evidence now that all of those cells are free. And so we're gonna rasterize the ray onto the map and determine what those cells are, all those free cells, and we're gonna subtract some log odds from each ray cell that the ray passes. All right, so this is our map update algorithm. We have a scan, we have a pose, we have a map. All right, so for each ray in that scan, we're gonna find the endpoint and then update the map with the new log odds. And then we're gonna take that ray and we're gonna project it onto the map to figure out which cells it passed through, okay? And then for each cell that it passes through, we're gonna update the map with the negative by subtracting off the miss odds, okay? So looks like this. We get our LiDAR ranges and they're in the form of some distance and some angle, right, relative to the robot frame. And so we need to turn that into a global cell position in our map, and then the endpoint and a global cell position in our map, and all of the rays that it goes through to positions in our map, okay? And we give you a set of utilities for converting between poses and occupancy grid map locations in the file grid utils in the repository. All right, so that's all handled for you. But we have a hit, and then we need to update all of these misses. And then we'll step through for all of the rays for every single LiDAR scan we get. All right, so there's two ways that we have sort of stem functions, empty functions for you to do the update of the ray, right? And so there's sort of two ways to think about this. One is you can divide and step along the ray. So you figure out the direction the ray is going and you step sort of a half cell width along and check which cell that ended up in, which point that ended up in. And so doing it this way, you need to sort of step along this line, figure out which cell it maps to, and then ensure that you don't double count any cells, right? Because if we're double counting cells, we're going to decrease the log odds more than we expected to. Okay, so for this, right, we're going to need to use some trig functions, cosine and sine. So we're going to need to do some floating point math, right? And that might take a little bit longer than some other way. So the other way, the other recommended way we have you cast the ray, which is sort of the classic ray casting algorithm, is Bressingham's algorithm. All right, so the idea is that we're going to convert this into a simple integer problem where we find the distance between the x distance between the cells and the y distance between the cells. We need to keep track of the sign, the slope, right? Because depending on whether we're going up into the positive quadrant or down into some negative quadrant here or this direction or that direction, it's going to adjust the algorithm just a little bit. So we keep track of SX and XSY. And then we have some total error. And eventually, we want that error to go to 0. All right. So we start out in our initial point, and then we're just going to check our error to determine whether we're going to step in the X direction, right? Or the Y direction, or maybe both. So step in the X or step in the Y or both. And so as you do this, you will basically find all of the cells that drawing this line on the map would touch, right? If you're writing a computer vision program, you might turn those cells black to draw a line. And then just add those to a set of points, right? And then we can do the log update on those points. All right. So here's the code that we give you, all right? The update map function. This is in mapping.cpp in SLAM, all right? It takes in our MBOT's LiDAR scan, the message, our LCM message from the LiDAR, our LCM message given the pose, and then our current map, all right? Obviously, if we've never run this before, we need to make sure that we have a previous pose. But once we have a previous pose, we're going to call this moving scan function. And we'll talk about this in a little bit and what this does. But this will return a set of laser rays that you will then use to update the map's log odds using this set of laser rays. All right. And you need to both consider the cells that the laser hit, right? The endpoints of all of those rays, and also the cells that it passed through. All right, so why do we need a moving laser scan? Well, as we're driving along, right, the laser is rotating and giving sensor measurements, and all those sensor measurements are at different times than the poses that we're at, the robot is at, right? So it might even be, you might even have a situation where the robot is driving along in a straight line, right? And the scan starts at one pose and then swings around and then ends at a new pose, all right? So what we need to do is align up all of our poses with all of our laser rays, so we actually know where that laser ray began in space, all right? And the only way to do this, because we don't have so many poses and so many lasers, is to interpolate between them. So what we're going to do is we're going to interpolate the odometry readings that we have, and so that we can align them with the laser scan times. So each ray will have its own timestamp, and what we want to know is where the robot was when that particular observation was taken, all right? And so to do this, what we have is what we call the pose trace, and this is implemented for you in common posetrace.cpp. But the idea is that we're going to add all of our poses from odometry to some vector, and then it has functions to access an interpolation of X, Y, and theta based on the timestamps that were in the odometry and the timestamp that we want out, all right? So if we go back and look at moving laser scan, we pass it a scan, we pass it the previous pose, that is the last time we ran this map update, and our new pose. And so we're assuming that the scan started when we were at the previous pose and ended when we were at the current pose. All right, and we do this based on looking at the timestamp of the laser measurements, right? And the timestamps of our odometry to figure out where we are, where the laser scan happened in space. And this will return a set of ranges, R and theta, with origins. So it'll give it, you'll have the actual origin of the ray to go through. All right, so check out the moving scan stuff. Actually, you'll need to write it, right? So here's a moving laser scan. You'll need to implement this. basically you take in your LiDAR scan and then two poses, the start and the end pose, okay? And then we check, we go through each of those ranges. There's a weird check that they're greater than 0.1. I think I asked Shaw to remove that or change that, but just note that this is here. So you might want to check if the rays are valid before doing this. So what would be an invalid ray? Maybe it hit max range and you don't really want to consider it, right? Or maybe it's too short, which is what this is saying. If it's less than a robot radius, it's too short. Now with the current version of the MBOT, I don't think the LiDAR can read a range less than the current radius of the robot, so you might not need to do this. But then you need to calculate the ray pose by using this interpolation function. This interpolate pose by time is something that is in common post trace, or one of the common. It's a function that we give you. It's in the library. And then compute an adjusted ray. So you'll populate the values, the start, the origin, the range, and the angle for that adjusted ray. And then it just gets pushed back into some list of elements and then returned, right? So we're going to return this set of adjusted rays that we're going to use in our update map function to update all the cells. So you can start with, we have a set of log files, which if they're not posted yet, will be posted. Those log files have motion capture data in them. So we have the actual true pose of the robot. And so if you run the SLAM system with the flag mapping only, it will, and give it a log file, check the help in the SLAM program for how to run that. You can then just map and use your algorithm for update map and your algorithm for moving laser scan, right? And the actual ground truth poses that we took from the motion capture system. And you can build a map, and you should be able to see a nice map of some environment that we built a while ago and took data on. And so that's how we're going to ask you to test your mapping, is to use some log files that we've already taken. Later, we're going to see how next time, right, we're going to look at localization. So this mapping algorithm assumes, right, that we know exactly where we are in space, but that is not necessarily true. We don't know where we are in space unless we haven't moved yet, right? Because when we start, we know where we are, we're at the origin. And then as we move, we don't really know where we are. We have an estimate of where we are because we do calculate the odometry. But if you were to take all the laser scans and just use the odometry as your pose, do you think you're going to get a nice crisp map? Yeah, no. So next time, in the next lecture, we're going to look at localization. And so we're going to look at being able to figure out how good an estimate of a pose is by looking at the sensor information and whatever map that we currently have. And so when you add these two together, you basically iteratively just update your map and then update your location. And then you update your map again using the location you just found, and then you update your location using the map you just found, and so on and so forth. And that is simultaneously localizing and mapping. So that is going to be our full SLAM system. All right. Are there any questions on today's lecture? Yeah.
Like part of your mechanism blocking the LiDAR, and you just go to more like points within the range, you should still be able to get a pretty good mapping, assuming your robot turns that map that like included in your vision, right?
Sure. Yeah. In fact, you probably don't even need to worry about doing that on purpose, right? You don't necessarily need to turn just to map an area, because as you move around, you're going to see the area with your map. And in fact, a lot of these, maps and early robots that are making these maps, their lidars aren't 360 degrees. You can still make this map even if you only see, a little bit in front of you, right? Because you can just sort of move around and you're still able to make the map. Now, is it easier to do when you have all of your rays? Yes. And you'll also probably have to make sure you know which sort of ray angles from your laser scan are occluded, so you make sure you don't include them in your update, right? That would be here. That could be, you can do it a few places, right? But that could be here in moving laser scan, potentially, where you're figuring out what a valid ray is. Any other questions? All right, great. Well, hopefully you'll be done soon with your motion control, and you'll be able to start soon on the mapping. I would recommend that maybe one person in your group, if they're not really busy with motion control, get started right away, figuring out how this mapping works and how to run the logs so that you guys can quickly make progress on the SLAM system. All right. Thanks, everyone.